welcome back to Class 5 of Spring 21 ME470. And this is going to be Class 4. We're going to do a planetary gear, but we're going to look at the forces. This is problem 1332 from, I think, probably like the 9th edition or 10th edition. So we have 24 tooth. The pitch is 6. It's got a 6-dimensional pitch teeth per inch there, and a 20-degree pinion. 2 right here with 24 teeth. It rotates clockwise at 1,000 RPM, and it's driven by a 5 horsepower motor. So there's 25 horsepower coming in at 1,000 RPM right there at the sun gear. The other gears are 24 teeth, gear 4, 36, gear 5, and 144 is the ring gear right here. These are internal teeth. So what is the torque? What torque can arm 3 deliver to its output shaft? Now notice from the figure there's this little gray part right here. That means that the ring is fixed. Okay, so we want to know what torque can the arm deliver. So the arm is going to be the output of this. Draw free body diagrams of the arm in each gear and show all the forces that act upon them. Right. So we want to try to figure out where all the forces are. We could actually figure out the torque based on just we could find the input versus the output RPM, because the power is going to be equal in and out. So if you know the RPM, you can find the torque, right? If you have the power and the RPM, you can find the torque anyway. I have I guess this is not an animation. That's too bad, because I lost the SolidWorks files here. But you can kind of see this is the arrangement of the thing, right? This would be the input shaft right here. This guy that's driving this gear and the sun, and then this would be the output because it's connected to the arm. All right, so let's take a look at writing this thing out here. First thing, good idea is to figure out what all the speeds are going to be. That just kind of helps. So let's say we have an E right here, where this is let's call this the driver. So it's going to be N2 drives N3, right? It's going to be the denominator here, and then wait, sorry, they're calling the arm 3. Right. Okay, so 2 drives 4. That's right. And then 4 drives 5. And then 5 drives 6. We should establish what direction it's going to be. If we hold the ring in, we want to hold the arm. We hold the arm in place. And so I like to draw them this way. We got to. Right, this one is going, they said it was going clockwise, right? They said it was 1,000 RPM. Clockwise, yeah, clockwise. This is going that way, so that's going this way, which is going that way. So that's coming this way, it's coming this way. And that's going to, even though that's clockwise right here, that's going to drive this outer one clockwise. So it's clockwise input, clockwise output. That should be positive. So we go, and by the way, that cancels out that cancels out that. So all we really have to do is just take N2, which is going to be 24, right? And divide it by 144. So we have a 0.1667 is what the gear train ratio is going to be. Now if we want to find what the output shaft is going to be right here, we take our last minus arm divided by first minus arm. My voice is very low today. Talking very low. I wonder why that is. Okay, so this one is the last, and it is fixed right there, right? So we just have negative NA, which is going to be the arm, and we have 1,000 RPM. Let's just use positive as clockwise. That's not typical, but as long as we know what we're talking about here. And we set it to 0.1667, right? And then we could solve for NA. And we get that it's going to be a negative 200, okay? So that means that this is 200 RPM counterclockwise, right? Now we have it, and that's going to be, did I call it something? I guess I called it gear, I guess I called it 3 right there, right? Because it's 3. It's just going to help with the numbering of things when we go to do forces, right? Instead of using letters, we'll use forces. We'll use numbers for the subscripts. So we should figure out what the diameters are of this, the different gears. Let's see. Well, the second gear, the diameter second gear, is going to be equal to the second, the diameter of the fourth, because they both have 24 teeth, right? They both have 24. They have a 6 pitch, right? So you take the number of teeth and divide it by the pitch. So 24 divided by 6, and we get that these are going to be a 4-inch pitch diameter. I don't know why I started using the double the quotation mark for the inches, but I did. The diameter of the fifth gear, that's 36 teeth, 6-inch diameter. And then the last one, let's call it D6. Yeah, D6 is 144 inches. That comes out to 24 when you divide it by 6 teeth per inch, right? Let's get the pitch line velocity on the input. So I'm going to say it's the pitch line velocity of 2, which is the same thing as the pitch line velocity, and this pitch line velocity of 2 and 4, right? They share 2 and 4. They have to have the same pitch line velocity. So I guess I decided to write 2, 4. I'm not sure if that's like a solution manual thing that I'm mimicking. The pitch line velocity, look up the equation, the definition right there. Should be familiar with it. Got pi over 12, 4 inches and 1,000 RPM. Give us 1,047.2, and these are feet per minute. And that's just what the U.S. customary units they end up using for AGMA, pretty much. So then we can find what the, let's just use their designation. This is going to be the force of 2 onto 4 in the tangential direction. We're going to use the equation 33,000 H over V, right? And it's got to be the specific one, right? This is the velocity, pitch line velocity 2, 4, and what we end up finding is we get 33,000. 25 horsepower divided by our 1,047, and I get 787.8 pounds. Okay, so that's going to be the force on the pitch line velocity. We could do this in a whole bunch of different ways, by the way, as we're trying to figure out what force is. And I decided to also use an equation 342, right, to find the torque, right? So the equation is H is 2 pi Tn over 33,012, right? So that's equation 342 for back in chapter 3. And I don't want to say equals because I'm going to try to find the torque in and the torque out. So I wrote the torque in is going to be 33,000 times 12 times the power 25 divided by 2 pi and then the RPM, or 1,000 right there. So you get 1,575.6 inch-pounds, right? Well, the torque out, right, so that was the input shaft, which I've indicated is this guy right here. The output shaft is going to be connected to the arm. So we could just use all the same things here, 25 horsepower, but the difference here is going to be that the output shaft is at 200 RPM. So you can get that to be 7,878 inch-pounds, right? So because this went from 1,000 RPM to 200 RPM, right? We have essentially this is like a 5-fold, right? Is that true? Right? If we went from 1,000 to 200, we reduced by 1/5. So we multiplied this by 5 right up here, right? We've increased the output torque, decreased the output output speed. I think I can do this later right here, but I'm going to draw my free body diagrams of each of the components, right? So I have 3 components that I really care about. I'm going to leave the ring alone. So I'm going to go this gear. This is sort of like an idler, and you could call this the planet. I guess you can call both of these the planets, and this is the ring, right? We'll leave the ring out. So we'll just use the sun, this planet, and this arm. We'll do the free body diagrams of them. So let's see, I'll write these out right here. I'll give it like maybe a little bit of proportion to the thing. Okay, and so in this FBD is going to be gear 2. And I'll write over to the side that that's going to be the RPM right there. That's not necessarily part of the free body diagram. But okay, so if this gear is running clockwise, then the gear, it's pushing down onto this gear, right? So it would be giving a force right there, and this force would be the tangential force of 2 onto 4. There would be a equal and opposite one that's resisting this. This would be the tangential force of 4 onto 2, right? And that would be equal to this force right here. There'd also be radial forces as a consequence of the pressure angle, right? So there's the radial ones of 4 onto 2, and here is the radial of 2 onto 4. Okay, so what's going to happen here is there's a torque that's driving there. You can see the sum of the moments must balance out. So we have the torque that's being placed right onto there, and that's going to be the torque of, what did I decide? I just decided to call this torque in, although we could have called this, we didn't number or name the shafts, right? So this could, if that was shaft A, we could write that this was torque A onto 2, right? Because it's an external happening onto there. There's also reactions, and these are all the forces that are happening on here. So the reaction is actually going to be downwards, and it's I guess I'll draw it this way right here with the arrow. Sometimes I'll go over to the side, and that's not really a good place to label the torque, so maybe I'll try to put it up here, torque in up here, and then up over to here above. I guess I decided to write this F, I guess I did call it A2, and this is Y, and this was F A2 X right in there, kind of cramming it in. I kind of almost want to have that as A2, so let me say, I'll leave it as torque in, that's fine. Okay, and then so right in here, we have to have the, okay, so what happens next? Well, we could do this in a bunch of ways. One thing that we would know is the pitch line velocity here has to be the same as the pitch line velocity right here. It just has to be. I mean, you know, it's, okay. So, and the power in has to equal power out. So these have to have the equal force. Another way to look at this is that this one, the torque has to balance out here. There's no external torque being put into the shaft. This thing is just spinning on its shaft freely right here. So that means that the out of this has to equal that. And also, if that's going counterclockwise, there has to be a force that's trying to go clockwise that balances the thing out if we're running at a constant speed, right? So that means goes down that way, and then this force is coming in here. And this is going to be let's see, this is number 4, this is number 5. So this is the force of 5 onto 4 in the tangential direction. And then this is the force of 5 onto 4 in the radial direction, right? Now you look at this has to equal that has to equal this. So there's no, some of the forces in the x direction, there's nothing that happens here at the axis, but this one right here has to be pushing back at, and this is going to be the arm right here, right? So this is well, there's actually a shaft. We could say that the shaft is connected to the arm. That's fine, right? So we'll say that this is going to be F of 3 onto 4. And I think I'm going to say this is in the y direction, right? So this is the y direction right there. And I should write that this is the FBD of gear 4. Now I write the FBD of gear 5. That's happening right there. Once again, we're going to have the force here. The pitch line velocity here has to be the same as the pitch line velocity there. So we have to be coming up equal and opposite forces right there of gear 4 onto gear 5 in the tangential direction, and then gear 4 onto 5 in the radial direction. And then lastly, we can see that there's no torque that's going to be coming in here, so this has to be 4 onto 5. Oh, this has to be 6 onto 5. 6 onto 5 in the tangential direction. Did I do that right? Yep. And this is force of 6 onto 5 in the radial direction. So what's going to happen here is we're going to have a force that's coming in that direction right there, which is going to be the force of 3 onto 5, and I'll call it in the y direction. Let me double check this right here. Okay, yes. So what if we take the sum of the forces in the y direction here and the sum of the forces of the y direction there, what we're going to find is the sum of the forces in the y direction equals 0. I think I'm going to go ahead and just write this out, that we know that this right here, F34 in the y direction, is going to be 2 times this value right here. So we could write out that F34y is going to be equal to 2 times F24. That's 787.8, right? 787.8. And that's going to equal 1,576 pounds. The same thing true right here, that F35 in the y direction, but just opposite, is also going to be 1,576 pounds. So now we go down to the FBD of arm, and it's called 3. And we take a look what's taking place here, right? Now this is connected to some shaft, and I'm going to place it, the output shaft. You can see that I've aligned it like right in here. So we're looking at this thing right in here. It's going to have some bearing that supports it right there too, by the way. But if we take a look at this force, is going to be applied right here, right? Well, we have to be careful where these things are located. So before I go any further with this, I want to get the dimensions, right? So there's going to be a location right there and a location right here. So these are going to be the gear centers. So I have the diameters up here. I guess I'll put it over to the side maybe and say that I have C24. All right, so this is the distance between gears 2 and 4. It's going to be this C24, like right in there. It's going to be the diameter of 2 plus the diameter of 4 divided by 2. And so that was, remember, let's see. Did I have that right? Where we said, yeah, this was 24 teeth and this was 24 teeth, right? 24 and 24. And so both of them, 2 and 4, are both 4 inches right here. So 4 plus 4 over 2, 4. Yeah. And then C4 and 5, right? Those are going to be D4 plus D5 divided by 2. Or the diameter of 5, what did we say? That was 6 inches. 6 inches, right? So that's going to be 4 plus 6. So that's going to be 5 inches right there, right? So we'll say that this is 4 inches right there, and this is 5 inches. Something we need to know. Now, apply the forces here. This force is upwards, and this is 3 acting on 4. So this one right down there is the force in the y direction of 4 acting on 3, which is equal to 1,576 pounds, right? Same thing down here. This one is the force of 3 of this acting on this. So this one is acting on this one at 453y. And now this is the output shaft. So it has to have a reaction right here that's going to balance these two things out. Now, we happen to know that they're equal to each other, right? So actually in the y direction, it's not going to have a, I think actually in the y direction, it's, yeah, actually right here, we're not going to have any forces onto there. We could put them on there because in reality, there's going to be some reaction the bearing has to have for, you know, the dynamics and whatever is the thing is a changing position, that kind of thing. But they all kind of, they cancel each other out there. And there's no x coming on here because this one cancels out that one, this one cancels out that one. So we're pretty golden when it comes to that. But there's also going to be a torque, right? So this is causing a torque clockwise, and this one's coming in causing a counterclockwise. So this one, but this one has a longer distance. This only has 4 inches. This has 9 inches, right, to cause a counterclockwise. So the output torque, or the torque, I should say, of the load that's happening onto this right here, this torque out is coming in that direction. And I need a piece of paper. What did I do with all my paper? I don't know. I like having a clipboard around. Clipboards make things better, right? Well, I didn't cram, I did all that work to cram the stuff onto one page, and I still didn't manage to get it all on one page. Yeah, oh well. So if you take the sum of the moments, and you take it about, let's call this A, right? Take it about A. Say counterclockwise is positive right here. You could say, okay, well, the torque out is negative, just the way that it's drawn, right? Because it's shown as clockwise. And you're also going to have this force right here that's also clockwise. And we know that force is 1,576, right? And that distance is 4 inches. But now we have this force right here is going clockwise of 1,576 again. But now it's going to be 9 inches. and that equals 0, right, to balance out. If you work all that out, you get 7,880 inch-pounds based on the forces, balancing all the forces out. But of course, we had the output RPM and we had the power, so that's what we predicted. So it balances out. It's so this is a good demonstration of how to work through a force situation, and then also to have two different means of checking your answer. Input and output torques. Yeah, so there you go. I think it's a good example. Long example.